Hello, my name is AllisonHarvey, and this video is going to focus on some basic concepts surrounding optimization. So starting off, it's important to understand what the objective of optimization problems are in calculus. So the objective of optimization problems are to find the dimensions that can minimize or maximize an object's area, volume, profit, whatever it may be, depending upon the problem. So in optimization problems, we are often given a constraint equation and an objective equation. The objective equation is what we are often trying to maximize or minimize. So the constraint equation helps us to solve for a term that can be substituted into our objective equation. So I'm going to explain this a little bit further on this next page. So continuing with our concept, this example is going to show us what it really means to have a constraint equation and an objective equation and how they relate to one another and really help us to solve optimization problems. So continuing our concept, they want us to find two numbers whose sum is 60 and whose product is a maximum. So what do I know? I know that the sum of two numbers is 60, so I'm going to write that equation. Sum equals x plus y. Okay? And they want us to find the product. So product equals x times y. Okay. Now, they told us that my sum is equal to 60, so I'm going to write that in. 60 equals x plus y. Stop. This is the constraint equation. It's the constraint equation because I'm given a constant. And I can use this to solve for one of my terms that can then be plugged into my objective equation. So that's exactly what I'm going to do. I'm going to take 60 equals x plus y, and I'm going to solve for x. So 60 minus y equals x. Now that I have a term that is equivalent to x, I'm going to plug it into my product equation, which is normally product equals x times y, but I'm going to plug in a value that's equivalent to x. So product equals 60 minus y, because we just found that to be x, times y. Now I'm going to distribute the y term, so product equals 60y minus y squared. Now, the purpose of optimization problems is to find the max or min of a given situation and to find its dimensions. So that's what we're going to do. We're just going to take the derivative of this objective equation because this is what we are maximizing or minimizing. In this case, we're maximizing it. And I'm going to take the derivative, and then I'm going to set it equal to 0. So p prime is going to equal 60 minus 2y. Now I'm going to set it equal to 0. So 0 equals 60 minus 2y. All I did was set my derivative equal to 0. The next step is to solve for y. So I'm going to move my 60 over, so we get negative 2y equals negative 60. Go ahead and solve for y. Y equals 30. This is perfect, but we're not done yet. I can plug this value of 30 into this equation that we found earlier to find my dimension for x. And then, having both of these terms, we can find that product. So let's go ahead and solve for x. So we have 60 minus y equals x. We found y at 30, so let's plug in 30. So 60 minus 30 equals x. So x is 30. So to find our product, we're going to multiply these two dimensions by one another. So we're going to say p equals x times y, or product equals 30 times 30. So our product that is a maximum is 900. Alright, now that we understand what a constraint equation and objective equation are, and just some basic ideas behind optimization problems, we can really look at an example and begin to understand the ins and outs of the concept. So this is our example problem, and they say that they want us to find the dimensions of a rectangle with a perimeter of 100 feet and whose area is a maximum. Okay, let's dissect this question. What am I told? First of all, they want me to find the dimensions. Okay, keep that in mind. Dimensions, not area, not volume, but dimensions. So maybe we're solving for x and y. Let's keep that in mind as we go about. So find the dimensions of a rectangle. Okay, I'm dealing with a rectangle. I know that a rectangle is x by y. Okay, with a perimeter of 100 feet. Well, I know that p for a rectangle equals 2x plus 2y. Okay, and the perimeter is 100 feet. And whose area is a maximum. Okay, I already know that I'm going to be maximizing my area, so that's my objective equation. Alright, now we can go about this problem. First thing I always like to do is draw a diagram. So that's exactly what I've done. I've drawn a rectangle, and I've given it the dimensions of x and y. Just helps me to see it visually, and helps me to make sure I don't mess up my perimeter equation. So perimeter equals 2x plus 2y, and they told me that that is equal to 100. It's equal to a constant. This means that this is my constraint equation, and I can use this equation to solve for a term that can be plugged into my objective equation. So I personally want to solve for x. So I'm going to say 100 minus 2y equals 2x, and I'm going to go ahead and divide everything through by 2. So that's 100 minus 2y divided by 2 equals x. So 50 minus y equals x. Perfect. Now I can plug this equivalent form of x into my area equation. And the area of a rectangle is area equals x times y. So we're going to plug in the equivalent form of x. So area is going to equal 50 minus y times y. I'm going to go ahead and distribute that y term. So area equals 50y minus y squared. Now, since we're maximizing the area, I'm going to take the derivative of the area, which is going to be 50 minus 2y. I'm going to set it equal to 0 so that I can solve for y. So negative 50 equals negative 2y, or y equals 25. But I'm not done. I also want me to find the dimensions. I only have one dimension. Now I need to solve for the x dimension. So going back to the perimeter equation, I'm going to plug in the y value that we found, which was 25. So 100 equals 2x plus 2 times 25, or 100 equals 2x plus 50. I'm going to subtract 50 from both sides, so I get 50 equals 2x, or x equals 25. So the dimensions are x equals 25 feet and y equals 25 feet. And we have solved this optimization problem, and we have debunked this often complex concept of calculus.